happy to have Dr. Clara Burgard. She's a postdoctoral scientist at the Institut des Géosciences et de l'Environnement at University Grenoble, Alps. She studies interactions between ice, ocean, and the atmosphere, and also explores ways of communicating scientific research to peers and larger audiences. Dr. Burgard earned her PhD from the Max Planck Institute for Meteorology and the University of Hamburg, where she examined the relationship between observed, simulated, and real Arctic Ocean sea ice concentrations. And following her PhD, Dr. Burgard also served as a scientific coordinator for the Earth League, which is a voluntary alliance of prominent scientists who advise decision makers about environmental issues. So today she will be speaking on the topic of ocean-induced subshelf melt, using cavity resolving ocean simulations to assess existing parameterizations and explore deep learning approaches. So welcome, Clara.
Thank you very much for the introduction, Patrick. And thank you very much for the invitation anyway. I hope you can all hear me and see me. Yeah, perfect. Now I did the same mistake as always. Okay. Okay, so yeah, as Patrick said, I did my PhD on sea ice, but now I have spent a bit more than 2 years on ocean-induced subshelf melt in Antarctica. And I want to present in the next 30 to 40 minutes two things. So one is a publication that came out in December 2022 on existing parameterization of subshelf melt. And the other is a glimpse into what I am currently working on. So I was not completely sure how diverse the audience is. So we're going to start very basic, but also very quickly. So what are ice shelves and why are we interested in them? So ice shelves are the floating ice tongues at the margins of the Antarctic ice sheet. So they represent the place where the ice sheet meets the ocean and starts floating. And why are they important and interesting? Ice shelves buttress the ice flow from the grounded ice sheet to the ocean. And this way they moderate how fast grounded ice lands in the ocean, and therefore they moderate the rate of mass loss from the Antarctic ice sheet into the ocean, which essentially is that they moderate the pace of sea level rise at the moment, especially. And so with climate change, there is warmer ocean water that reaches the cavities below the ice shelves, so that there is less or the ice shelves melt and thin and retreat, and therefore there is less buttressing from these ice shelves, and so they can less buttress the ice flow from the guarded ice sheet to the ocean, and therefore there is a risk of a faster pace of sea level rise. So they actually play an important role for understanding the future Antarctic contribution to sea level rise. And so ice sheet models need the information about this ocean-induced melt at the base of the ice shelves to force these models to project what the future will look like. Ocean models also need the information about the melt because it affects the water properties in the cavity and therefore also the water properties in front of the cavity. But we have quite a big challenge or a big problem at the moment is that typically these subshelf cavities are shown here are typically not resolved in ocean-uncoupled climate models at the moment. So the link between the open ocean in front of the ice shelf and the ocean ice sheet interface is missing. So this problem is not new, and I'm not here to say I'm reinventing the wheel. Basal melt parameterization have been developed in the past decades to bridge the gap between ocean temperature and salinity as given, for example, by observations or models without a cavity, like coarse climate models in front of the ice shelf, and the basal melt rate at the base of the ice shelves. But here again, challenge as always, the evaluation of these parameterizations is challenging because what you normally do when you have a model is that you want to evaluate it against observations. But in this case, we don't have many observations that we can use to do that, because for the ocean temperature and salinity in front of the ice shelf, we need in situ observations, and there are not many. And the ones that are there are irregularly distributed in space and time, so maybe just in front of a few ice shelves, and we don't have continuous time series. For basal melt rates, it starts to look a bit better. So we have satellite melt estimates existing now, but they remain uncertain because they include a lot of assumptions and also models about what is happening on the surface. So another approach to evaluate this parameterization is to use a model where we would know everything that is happening here, that is happening here, and here. And so this was done in 2019. An assessment and tuning was done within an idealized coupled ocean ice sheet model simulation. But then when people wanted to use it on the circum-Antarctic level, it came out that this tuning was probably not representing a high enough diversity because empirical corrections were needed for different regions, which means that the tuning seems to depend on what you use it to tune. Still, it seemed like a nice approach to get into the evaluation of this parameterization. And so what we have been working on is to use this approach, but on a circum-Antarctic level, by using circum-Antarctic cavity resolving ocean simulations that we use as a virtual reality to assess and retune existing parameterization and then explore the potential of a deep learning parameterization. So before going into the parameterization, I just quickly want to present what our virtual reality looks like, because it will be our reference for the rest of the talk. And I hope that you can be convinced that we can use it as a reference, keeping in mind that is virtual reality and a model. So our virtual reality is an ensemble of 4 NEMO global ocean simulations. So these are simulations that were not conducted on purpose for this study, but they were conducted for another project. And so we had them anyway. And we thought, okay, then if we have them, we can use them for our study. They are resolved on a 1/4 of a degree grid. And in total, they represent 127 simulation years, representing varying conditions between 1980 and 2018. In these simulations, the 35 largest cavity are resolved. These are the one that you can see here in white on this map. And resolved means that the ocean circulation works in the cavity and that we also have resulting basal melt. So these simulations give us ocean temperature and salinity in front of the ice shelf, as would be given in application cases from observations or from coarse climate models. We transform them into profiles averaged over a given domain in front of the ice shelf to make it easier as an input to the parameterization. And then these simulations also give us the basal melt rates that result from these properties in front of the ice shelf. And so we can play around by putting melt parameterizations here in between to compare what comes out, kind of. So this is our virtual reality. Let's go to what we did with this. So to the assessment and retuning of the existing parameterizations. And for this, I want to start with getting on the same page on different definitions. So for example, what do we mean by tuning? We tune on minimizing the root mean squared error between the parameterized and the reference yearly integrated melt on the ice shelf level. So what does this mean? We take ocean temperature and salinity for each year from the NEMO simulation. We put it in the melt parameterization, which gives us then a melt at each point. Then we integrate over the whole ice shelf the melt, and we compare it to the target integrated melt rate also over the whole ice shelf. And by minimizing this difference, we tune the parameters of the parameterizations. But the tuning and the evaluation actually might be biased, we saw it already before, might be biased by what we used for tuning. So to make this a bit more robust and maybe find out what is important when we tune and evaluate, we do this with cross-validation, where we divide our whole data set into different blocks. So for example, we have 35 ice shelves, so we divide into blocks, 35 blocks, and then over time, we have 127 years. And we decided to divide them in blocks of 10 years so that we avoid bias due to autocorrelation in time. Because if you tune on, for example, 126 years and then you evaluate on one, then this one is very close to something that has already been tuned on. So this might give too optimistic results. And so if we do the cross-validation over time, we tune over 12 blocks of 10 years and we evaluate on one. And then we reiterate this 13 times until every time block was left out of tuning once. And then we can do the same over ice shelf. So we do a cross-validation over ice shelf, we tune over 34 ice shelves, we evaluate over one, and then we reiterate this again 35 times until every ice shelf was left out of tuning once. Okay, so in the next slides, I will slowly build up my main figure. This is because it's a bit complicated, but I hope that by building it step by step, I will not lose too many of you, I hope. So now I have explained you what the different points will look like. This will be the cross-validation. And now I want to present which parameterizations we looked at. So there are different families. There is, for example, the family of simple parameterizations, where the melt depends on linearly or quadratically on the thermal forcing, where the thermal forcing is the difference between the water temperature and the freezing temperature. And for the quadratic parameterizations, you include information about a slope. So you can also define the slope in different ways. So we tried out what happens if we use a constant slope for whole of Antarctica, what happens if we use a cavity slope, so a slope for each ice shelf, and a local slope, which is the slope at each grid cell. Then there are more complex parameterizations, like for example, the plume parameterization, which assumes the formation of a buoyant plume and the grounding line, which then rises along the ice shelf, ice-ocean interface. Then there is the box parameterization, also well known as PICO, which divides the overturning circulation below the ice shelf into different boxes. And then we have PICOP, which combines the plume and the box parameterization by computing temperature and salinity with the PICO model, and then the melt rate using the plume parameterization equations. For all these, there are also several variations, but for clarity, I only show one. If you're interested in more details, you can look into the publication, but the main conclusion remain valid for all the variations of these. Okay, so that was which parameterizations we'll look at, and then these are the metrics we start looking at. So in the first step, we want to assess the influence of the input domain over which temperature and salinity were averaged that we give as input to the melt parameterization. So in one case, we averaged the temperature and salinity over the continental shelf within 50 kilometers of the ice shelf front. And in the other case, we took temperature and salinity off the continental shelf, but also within some distance of the ice shelf front, just to mimic what very coarse ocean model could give as input that don't even resolve the continental shelf. And so what we look at here is, again, the integrated melt. So it was the value that was used also for tuning. And what we will see is the root mean squared error over the left out blocks of the cross-validation. So every time this one block that was not used during tuning, and which is therefore like our synthetically independent data set to evaluate the tuning. So here are the results. So the first thing what you can see is that if we use temperature and salinity averaged over the offshore input, the RMSE is generally higher than if we use the properties closer to the ice shelf front, which is maybe not surprising, but it's nice to have it in a quantitative way. And then what we can also see is that the cross-validation over time, so that's the axis, leads to lower RMSE than the cross-validation over ice shelves, so both here and here. So this means that the tuning depends more on the ice shelf we used in tuning than the time blocks, and means also that the parameterization will generalize better over time blocks it has not seen rather than ice shelf it has not seen during tuning. Okay, and the third takeaway here is that if we have to decide on which parameterization is performing best in these two cases, we look at where both cross-validation lead to lower RMSE. And in this case, it would be the quadratic parameterization using a constant Antarctic slope or a local slope, and the plume parameterization. While for offshore, the RMSEs are much closer, but if we had to choose, we could say that the box and peacock parameterization and maybe the quadratic with the cavity slope lead to the lower RMSE. So from this figure, we can definitely conclude that using 50 kilometers input, if possible, is already much better than using offshore input. And so in the next slides, I will always show results using this 50 kilometers input. Just keep this in mind. So this was on the integrated melt, but especially for ice sheet modelers, it's not only the integrated melt that matters, but also where the melt happens. And so as a next step, we looked at the spatial distribution. So we looked, of course, at our 35 ice shelves, but for this presentation, it would be too much. So I just chose 3 ice shelves that are kind of famous, let's say. So we have the 2 largest, which are the Filchner-Ronne and the Ross ice shelves, and the Pine Island ice shelf, which is in the Amundsen Sea, where the ice shelves are retreating quite rapidly at the moment. And so this, what I show here, is the reference, so our virtual reality. And then here are the results with the different parameterizations. So here I don't really want to go into detail into each panel, but as a main remark over all this, I think everyone, when they look at this, you see directly that there is no parameterization that is clearly doing the better job. And actually, there are some ice shelves where really none gets it right. I think Ross is a good example for that, for example. Or here, for example, you see some parameterization do not really have some spatial heterogeneities, and here there's too much melt, so yeah. It is difficult to choose. So still, we wanted to have some metric that could give us insights, or a quantitative metric that could give us insight into what is better or worse, let's say it this way. And so what we chose was to look at the average melt near the grounding line, because the grounding line is the zone where often the highest melt happens, or also the melt is important for the ice shelf and ice sheet evolution. And so what we look at here is the root mean squared error of the space and time mean near the grounding line. So we took a box near the grounding line and we averaged, and then we do the root mean squared error. So here are the results, and we can see that the RMSE are actually quite close between the parameterizations, and the difference between the 2 cross-validation types is maybe a bit smaller. But then we have here 2 parameterizations that kind of get out and have very high RMSE. And one of them is the quadratic parameterization with the local slope, which with the integrated melt, we could have concluded is a good choice. So in this case, it seems that maybe it's not, it needs a bit more understanding what is happening. So if we have to do a conclusion here, and we want to use these 2 metrics as a basis of choice, the best compromise seems to be to use a quadratic parameterization using a constant Antarctic slope or a plume parameterization. So this was like the main result from the paper. If you are more into the technical details, we did also much more, but it's a bit boring to talk about it. So I would just recommend that you check out the paper. So you will find also best estimate parameters tuned on the whole data set. So not the cross-validation, but really on the whole data set. And then uncertainty ranges around the parameters. So we did some bootstrapping to test the uncertainty ranges around the parameters. This is a table showing the uncertainty range around the parameters from the simple parameterizations. And then for the complex one, they have 2 parameters instead of 1. So we sampled in both directions. And what we found for the plume, the pico, and the pickup is that there seems to be a relationship between the 2. So maybe in the future, if you want to tune them, it might even be possible to just tune one and then infer the other one with the relationship. This is something to think about. If you are even really in the coding, you can also check out our Python package. If you want to test the parameterization on your own data, I wrote the function so that if you have a temperature and salinity profile where you want to test it, it should work quite fast. So don't hesitate to check it out. Okay, and so for this part, if you got lost in the last 10 to 15 minutes, here is a very short summary of the main recommendations that you should take home from this. Is that 1, the continental shelf circulation matters, so better performances are there if you use hydrographic profiles averaged over the continental shelf rather than offshore. Then to choose the parameterization, you can either keep it simple or go for a complex one, so the quadratic parameterization using a constant Antarctic slope and the plume parameterization yield the best compromise for both integrated melt and the melt near the grounding line. If you only have offshore input available, then the comparably lower RMSE was reached with the box and pickup parameterizations. And finally, I think the main take home here is that circum-Antarctic tuning is tricky. We saw that most parameterization do not generalize well to ice shelves unseen during tuning, which means that your tuning depends on the ice shelves, and so that the parameterization cannot describe everything. And so circum-Antarctic tuning is not ideal. For some regions, it will underestimate the melt. For some, it will overestimate. So if possible, think about using the uncertainty ranges of the parameters that are also given in the paper. So here is again the QR code, how to get to the paper and the title. And then, then let's go to the second part, which is a much more exploratory because it's currently work in progress, but I still wanted to share and have some feedback. So we used the same virtual reality, but now to really explore the potential of a deep learning parameterization. Let me just check the time. Okay. So the idea is to train a feed-forward neural network to emulate NEMO. And I don't know how many are familiar with the neural network, so I always have the slide to a bit get you into it. So a feed-forward neural network works this way that you give it an array of variables here into an input layer, and then it goes through a given amount of hidden layers. You can choose how many, and also in each hidden layer, there are a given amount of neurons. Again, you can choose how many. And each of these neurons represents some weights. And then after each layer, you also have a function that introduces nonlinearity. So the more hidden layers you have, the more neurons, the more nonlinear it gets, but also the more weights it can have. I mean, there are pros and cons of having it big or small, but at least it is a nonlinear function that transforms your input array into your output, which in this case is only melt. And so what is special here is that I chose to do a feed-forward neural network, which is really applied for each grid cell. So it doesn't know what happens in the grid cell next to it. So there are no spatial patterns, and each grid cell is treated independently. There is another study that just came out 2 weeks ago by Rosier et al., where they used a convolutional neural network, which looks more at the patterns, but they have other limitations that, for example, they have a fixed size of the domain, and I wanted to have something that I can apply on my realistic ice shelves. So what gets into the our neural network at least is I wanted to keep it very similar to the parameterizations we had before, so that people could not complain that they would have to compute variables that they never had before. So I give it the ice draft and the slope of the ice draft and the bedrock topography and the slope of the bedrock topography. Then I give it the distance of the point to the grounding line and to the ice front, so that there is some information about where it is in the ice shelf. And then I give it, of course, the ocean temperature and salinity. So again, I use my mean profiles over the 50 kilometers in front of the ice shelf. And to have it on the same plane as the other variables, I extrapolate from the profile to the ice draft depth. So then this gives me a field where I have one temperature and one salinity value at each point. What gets out is the basal melt rate, no surprise there. But in this case, because it has no prior physical information whatsoever, we really train on the grid cell level so that it learns what to do with what it has been given. Yeah, so again, we do some training, same as before. We give it stuff from NEMO. It trains here, so then here it's neural network, and then it computes a melt rate, compares to the target, and then adjusts its weight until the difference is as small as possible. So here again, let's go back to a similar figure than before, how I evaluated the traditional parameterizations. So I have the integrated melt, the melt near the grounding line. Here are the 5 types of parameterization. And then I looked at different sizes of neural networks. So I start with an extra small version where I have no hidden layer, which is like a linear regression. And then I just tested out something from small, medium, large, and extra large, just to get an idea how this would work with my input. And so again, yeah, I have the same metric as before. This is the same points that we saw before, just as a comparison. And here's what it looks like with the neural networks. So you see it's not completely mind-blowing, but also there is some improvement. So first interesting result is that the linear regression definitely has a higher RMSE, so it makes sense to use hidden layers and nonlinear neural networks. So that's already nice that there is an improvement. And then when we use the neural networks, we see that the cross-validation over time really gets lower. So that's nice. But if we look at the cross-validation over ice shelves, we see that there is still, it's still much higher than the cross-validation over time. So there is still a problem that the neural network cannot generalize well to ice shelves it has not seen during tuning, which means that there is some information, that is proper to each ice shelf. If we look at the melt near the grounding line, the results are quite similar. I think this is because probably the differences are much smaller, so you cannot really see much. But again, the cross-validation over time leads to a very low RMSE, and over ice shelves, it's a bit higher. So we also looked at the spatial patterns. So this is what I just showed you before, just as a reminder. And here you have the results for the neural network. Here you see exactly what I just said. So the cross-validation over time, if you look at the patterns and you compare them to the reference, you see that they are really much closer than what we saw before. So if the ice shelf was present during tuning, the neural network seems to understand what to do at different time steps, or it just means that the variations in time are not too big. But here, if we look at the cross-validation over ice shelves, the pattern does not really look like the reference, although I would not say it's a catastrophe, but it's definitely not as good as here. So the neural network struggles to generalize to an ice shelf that it has not trained with. So yeah, we were with these results and we didn't really know how to continue. So we knew, but we thought we want to try something else. So one idea was, okay, maybe it overfits to some variables. So maybe if we put these variables away, it will maybe understand more of the physical links. So we varied a bit the input variables. So I took the medium variant and I just changed the input variables. So I did the cross-validation using, for example, only temperature, salinity, and ice draft depth. And yeah, that was the result. Then I did some other tests. I don't want to go into detail. I just want to show you the variety of results. So depending on the input variables, the results can really change a lot. For example, here we use the temperature, salinity draft, the distance to the grounding line, the distance to the ice front, and the water column depth. And from looking at the integrated melt, it looks actually quite good. But then if we look at the melt near the grounding line, we see then that the cross-validation over ice shelf lead to a very high RMSE. So this is not what we wanted, because the ideal would be to have both that lead to low RMSE on both metrics and both cross-validations. So from this, we could not really conclude that there was an ideal set of input variables. I also did a test just to compare again with other input variables, the size. So here I have the extra large. You see that indeed there is the RMC is getting a bit smaller here and here. So maybe it's a bit better, but yeah, I would not conclude that this is very significant. I need to work on this a bit more. But mainly this is just to say that, yeah, it depends on the input variables, and that there does not seem, at least from the one I tested, there does not seem to be one set of input variables that lead to clearly better results. So the step we now took was, okay, then let's go back to what we had in the beginning and say, okay, it doesn't generalize well to ice shelves it has not seen during tuning. But if it has seen, then it does generalize well over time. So does this mean it can also generalize well over longer time? That's the first question. And also, can it, or is it okay to take into account that it knows in which ice shelf somehow it is? And maybe this gives us like an advantage, at least for what happens if the geometry evolves, for example. So currently I am working on using, again, a simulation that has been already done. So a coupled ocean ice sheet simulation done for UK ESM. And in this simulation, we have a changing ice shelf geometry. So this would test if the overfit happens to the geometry of the ice shelf. So will the RMSE remain as low as for the cross-validation over time with an evolving geometry? And the simulation covers historical and 4 times CO2 conditions. So with this, we will also be able to see how the neural network performs with input data like temperature and salinity from a different distribution like climate change. So something it has really not seen during tuning. And even if we would move to observations at some point, we will not have these observations because this is climate change. So I'm currently working on it and I don't have the nice plots. So you will have to believe me when I say we can be cautiously optimistic, but unfortunately, yeah, I didn't make it to really have the nice plots. But it's okay. It's of course not as good as on the data it was trained for. That was very similar, but still, I was actually surprised that it worked actually quite well. So this is it. So thank you for bearing with me for so long. So the take-home messages are that we use an ensemble of cavity-resolving circum-Antarctic ocean simulations to assess existing and novel basal melt parameterizations. We show that the quadratic parameterization, assuming a constant Antarctic slope, and the plume parameterization lead to the lowest difference to the reference melt. And we show that a feed-forward neural network can produce integrated melt and melt patterns closer to the reference than the classic parameterizations, but we still further explore this to be robust. And before thanking you for your attention, I have a small advertisement block. If there is someone who potentially is interested, our group in Grenoble is looking for a postdoc of 2 times 18 months on the modeling of icebergs in the ocean model NEMO. This would be part of a European H2020 project, which is called Ocean Ice. If you're interested, you can scan the QR code or check out the link below. And of course, but you should be quite fast because you can apply only until February 27th. But also I have to add, it's only a CV and letter of motivation, so you don't need to involve other people for a letter of recommendation or so on. So it's really fast. Yes, so thank you very much for your attention, and this is it. Thank you very much.
Thanks, Clara. That was very interesting. Do we have any questions?
Everyone is just was too much information.
Yes, Letty has a question.
Hi, thanks for the talk. This was really cool. I just wanted to ask a little bit more about the stuff that's in progress. So I didn't quite understand, are you planning to train a neural network on that different model, or are you planning to use, say, the one that was trained on NEMO and then see how, if you use that as if you didn't have ice shelves, how well it would compare to the UK ESM that does have the evolving?
Yeah, so yeah, maybe I went through this too fast, but yeah, definitely. So I don't want to retrain it. I just want to use this simulation as like an really independent data set. So it still has NEMO and UK ESM. That's why we took it, because at least it emulates the same ocean model. But yeah, we want to use it to have like a different conditions. So the geometry is a bit different anyway from the beginning on, and then it moves. So the geometry as such will be different from our training simulations. And then there is this one with climate change, which also has other temperature and salinity. So it's really more of a test. And then we, in the conclusion or in the discussion, we can then say, okay, these are the limitations when applied to something else. This is what seems to work well, even on something that was not trained. But and if the conclusion is, okay, it doesn't work well at all for climate change, then definitely the recommendation would be, okay, maybe we should train it on climate change simulations, which will probably be one's conclusion, but I'm not sure how important, like how large the effect is.
So you'll use the input from UK ESM, get the melt rate, and then compare it to the computed melt rate. Gotcha. Okay.
Yeah,
okay.
Exactly. Yeah, sorry. Yeah.
Thanks. And then I also wondered if you think how good this 0.25 degree resolution NEMO simulation is, whether you've looked at evaluating that very much, or if you think there might be something that might be coming out soon that's better, or you think this is high enough resolution and not good enough.
Yeah, good question. So I think so quarter of a degree is already better than 1 degree.
Yeah.
We can agree on that. So I think the resolution is okay for the ice shelves we're looking at. I mean, we had this ensemble of 4 simulations, and we always compared them to observations or whatever we had as observations. It's not perfect, but yeah, estimates to see if we are in the realm of realistic patterns. And so we are, so it looked good. So this was already the first check. And then there is, of course, the limitation that also NEMO does some parameterization at the ice-ocean interface to infer the melt. So we use these 3 equations that are often used for that, but of course it's even more complex because it's turbulent and so on. But yeah, I think that that it is okay in the way that when you use my tune parameters as well as, for example, the neural network, you should always keep in mind that they were done to emulate NEMO, and that yeah, there might be some mismatch with observations, but I mean, our hope was that the physical link is tight between what is coming in and what is melting. But of course it remains a model, and yeah, this is just something to keep in mind when applying that. Yeah, maybe there is some mismatch at some point. And I'm not sure if a higher resolution is probably always better, because then you get better insight on the bathymetry and the circulation and all these turbulent eddies and so on. But yeah, this is actually quite limiting. Then you can do even less simulations, and then it's very difficult. So just out of curiosity, what resolution is models, or also ocean models?
Well, we have just at the moment we have Model-E coupled to PISM, the ice sheet model, but only for the atmosphere and only for Greenland. So we're just in very early stages about thinking about what we might do in the future. And I guess we had thought a little bit about using Pico, but it sounds like maybe there's not a lot of advantage to using that versus something more simple.
Yeah, I think this is always pains me a bit as a conclusion, because many people use Pico and it seems physically very kind of, it makes sense, but somehow it's, yeah, I don't know, at least in our tuning it didn't work well. I don't know. Also, I think it depends again also on the metrics you use for tuning and for evaluating. So maybe with another metric it would be better, but yeah, somehow it was a bit disappointing.
Any other questions?
Yeah, I guess I had a question regarding the first part of the talk. Hi, I'm pretty new to all this still, so excuse me if this is a dumb question, but when you're assessing the different simple parameterizations, as I was thinking about the local slope one, it seemed like I think it did well on like with an integrated value, but then it did poorly with like a local like melt rate at the grounding line. I was wondering if you could maybe explain like how it could do well in one sense but poorly in another. I guess maybe from like a more technical point of view, but then also just from like thinking about conservation, like if it's getting the integrated transport, the integrated rate right, and the local rate wrong, like where's the melt coming from, then that offsets that in another way.
Yeah, so this is a very good question. I'm not sure how far I can answer it, but I like to use this plot because for me it's the most clear. So I have to say, so a few years ago, so I'm also actually since 2.5 years new, but as far as understood, in earlier times for these big simulations, the linear parameterization was often used. Then some people suggest, okay, the quadratic might be already better. And then the slope was suggested only a few years ago, that having the slope would include more melt, because it was assumed that near the grounding line, the slope is higher. So that's how you would get highest melt there. But what you can see here, for example, is that, then, okay, good, you include the slope, but then somehow the melt gets way too high. So somehow this doesn't scale well. And I think that it works well on the integrated level is probably a product of that it was tuned on the integrated level. So somehow it seems to work well at balancing out things and at take into account. So for example, here it could be that this was then also important while it's not so important here. Or you can see here these very small things where there is very high melt. So then this would already be a high integrated melt for the whole thing, because there is not much melt in the other regions. So it kind of compensates, I think. Same here. Also, you see there is high melt here, but then nearly none in the rest. So I think for the integrated melt, why it worked well was that it kind of compensated through the tuning. But then if we looked only at one region, which was the one where there were the high slopes, that's where the melt was just overestimated. And that's how it can be. So it's probably, like a story of what happens near the grounding line and what happens in the rest, and how they are balanced, like how different they are, and how tuning would balance them, while only looking at one region will show that it's not well distributed somehow.
Okay, thank you.
What is kind of clear, I hope.
Any other questions? I guess I was wondering about the difference between ice shelves, like if there was more information or observations that might help. If there was like some other variable or variables that are related to different ice shelves, or why different ice shelves have different results.
Oh, okay. Yeah, that's so I must admit on this. Okay, so my paper is already like 65 pages in total. And okay, if I had gone into every ice shelf, I think this would have become a book. So I had to stop at some point. And when I had questions about individual ice shelves, I was just like, okay, no, I'm not gonna look at this. This will get me crazy anyway. Yeah, I think it's yeah, there are many things. So I think the most important difference, in my opinion, is actually, yeah, maybe I shouldn't show Filchner, Ron, and Ross as examples, because I think these are the most tricky ones, because I put just one averaged profile that is averaged over all this region, and I put it into this, and I hope that it will do magic and do my melts. But in Filchner, Ron, and Ross, there is circulation. There's water coming in on one side, going on the other. So there's a lot happening actually in the ice shelf. And I just give it one profile, and I'm like, okay, transform it into a reasonable pattern. So I definitely think that part of the problem is assuming that big ice shelf would behave like small ones. And probably if you get Filchner, Ron, and Ross out, the picture would already be different. I want to try this in the near future. Then there is the thing that there are some ice shelf where there is actually warm water coming in, somewhere this is blocked by fronts, so there is only cold water coming in. So this is called cold cavities, warm cavities. But this is covered kind of in our having all these ice shelves differently. But I think because we have only a few parameters to tune, this is maybe not enough to cover all this diversity of things. So I think that's so the size, the cold and warm cavity, and then, yeah, I mean, every ice shelf looks different somehow. It has different islands in the middle. I mean, it's all, yeah, it depends on the circulation that we completely ignore kind of because we cannot resolve it. So we ask these parameterization to do the magic, and we hope that through using the draft and the distance to the grounding line, we get something good. But yeah, it's still very simple. I hope this is I'm really speaking honestly, but in the way that I don't see anything else at the moment that could do the job as well, because you cannot run an ocean model for all the ensembles that the ice sheet models are doing. So you need some kind of parameterization, and yeah, so I'm very grateful that people have come up with them, at least.
We had a comment from Shaina in the chat. I think it's just a comment.
I'm sure I'll have questions once I read the paper, but yeah, I just wanted to say this was really such a great talk. Thank you so much for sharing, and I'm really looking forward to reading your paper.
Yeah, thank you. Good luck, and don't hesitate to ask me whatever is unclear, really, when you read it. No worries. Yeah.
Any other questions? Okay, I guess we can stop there. So thanks so much again.
Yeah, thank you very much again for the invitation. It was really nice.
Thank you.